Hi, everybody. Thank you very much for joining the Synthetic Intelligence Forum online session. My name is Vic Pant, and I'm very, very happy today to welcome an esteemed speaker, a world-renowned scholar, but also somebody who's got impeccable credentials of supporting large organizations and startups alike in the industry. If I was to introduce Professor Sanders in detail, it'll probably take another full Synthetic Intelligence Forum session. So without further ado, Professor Sanders, I'd like to welcome you on behalf of the Synthetic Intelligence Forum community. And we're very, very excited that you're going to talk to us about the intersection of quantum computing with data science. So the floor is yours, Professor Sanders. Thank you.
Thank you very much, Vic. I appreciate the opportunity to be able to speak at this session. And I'm very impressed by the sequence of speakers that have come and gone and the ones to come. So I feel very privileged to be able to talk in this session. And in fact, some of the things that I have to say probably will connect with what Jordy's talking about in an upcoming session. And I see you have other quantum talks planned. So I'm going to talk to you about applications of quantum computing to data science. And I'm going to try to give you a very unvarnished strategic view of what's going on in the field. The main idea here is that I want to talk about how quantum computing connects with data science. So first of all, data science is about capturing data, maintaining the data, processing it, analyzing, and communicating. So there's a whole wide range of things that happen in data science, and quantum computing can play a role in many different aspects. The idea of quantum computing is that we transform the foundations for data science, for computing itself. So instead of representing information by zeros and ones, we're able to make what we call superpositions. Some of us use the term quantum parallelism. Other people hate it because there's a lot of philosophical conundrums and all this to do with parallelism. But in a sense, we're able to create the informational states in a coexisting kind of way and co-process them. The idea is then that we're able to use a different kind of logic to process. So in computing, we use Boolean logic, and for quantum computing, we replace it by something that we call quantum logic. And I'll explain a bit in a moment. If I have the pictures, that will help, and if not, I'll just keep it in words. The goal in using quantum computing for data science is about a radical transformation of data science itself. So it's not about trying to make algorithms a little better, a little faster, or anything. It's about taking problems that can't be solved in the foreseeable future and making them solvable. That's the disruptive aspect. And the current state of the art in field is that we have the quantum computing field has now gone commercial. There are big companies like IBM. There's the middle range D-Wave, for example, in Burnaby, BC, and there's also a lot of startups. And so this talk is taking place virtually in Toronto. Xanadu is an example of a company based in Toronto that's using a photonic platform. So there are commercial computers available. These commercial computers, it takes a lot of time to get up to speed on being able to use them. Often they have their own software frameworks, their own way of programming, their own operating systems. And so at the moment, to try each one of these quantum computers, you kind of have to learn the vagaries of each system and then be able to test it. And each one operates very differently from another, and the benchmarks are quite different. Okay, so I mentioned to you about data science. I have a slide, but it's taken from the University of California, Berkeley. The School of Information has a nice summary slide of data science in 5 boxes, so I use that to communicate it. So I mentioned to you about the capture side of data science. Capturing is about acquiring the data entry, and so on. This is very subtle in the quantum computing aspect, because even the question of how the data is acquired, is it, instead of writing zeros and ones into files, one of the questions that comes up in quantum computing is how to interface it so that the data can go straight into some highly compressed but accessible, processable kind of database. In the processing side, there's data mining, classification, data modeling, and quantum computing can offer different features to help each one. Enhanced search algorithms for data mining, classification, data modeling that can make use of quantum processes to do models that are not obviously doable in classical computing. And then there's maintaining. And I want to mention the maintaining. There's a talk coming up in this series about privacy, and even storing data and how to store it securely is very important. And in that respect, quantum computers can act as a big threat. I'm just going to see, no, it's still, the PowerPoint's totally frozen, so I'll keep going as I am. Okay, so then the idea is that, as I mentioned, we have classical computing. So when I say the word classical, I mean it. We quantum physicists think of everything that's not quantum, we just call it classical. So that's what the word classical means here. The classical computing aspect is that we store things as zeros and ones. And I mentioned to you that in quantum computing, we can make a superposition. And I've tried to find an analogy for it. And the analogy that I have in mind is a chord in music. So when you learn to play music, you play a note. It's got a particular tone. But then you learn how to play a chord. And a chord on a piano, you press 2 keys down, and the right 2 keys can be harmonious. And so in quantum computing, it's as though each tone, the strength of that tone represented some information, and hitting 2 tones together gives this parallelism. So you can imagine a musical processing that would take these tones and map them to other tones. So the way it works in quantum computing is we kind of can only write, the information corresponds to different tones, but when you have music, you get interference between the different waves. And in quantum computing, we take advantage of that processing capability. But at the end, when you listen, it's like you're tone deaf. You can only pick up one tone. So the trick with doing quantum computing is how can we make use of the engine in the middle to be able to do really fancy things to process the information. But at the end, we can't see everything that happened. We're very restricted in what we measure. Okay, so, and I just wanted to give you another example. To try to give you the feeling for quantum computing. So there's the old story of Schrodinger. Raman Schrodinger was an early stage Austrian quantum physicist who tried to find ways to make quantum mechanics more acceptable. He tried to connect the idea of quantum mechanics to optics, but he ran into the following conundrum that showed that quantum mechanics is not really simplifiable. And so he considered the case of a cat in a box. So he imagines that that there's a cat in a box, and inside the box there's a poison gas, and the poison gas is triggered by a single nuclear decay. So there's different kinds of nuclear decay, alpha, beta, gamma, and in an alpha decay, the alpha particle can escape. And so he imagines if the alpha particle escapes the nucleus, the alpha decay, it triggers poison gas that kills the cat. But then he points out that quantum mechanics says that after a certain time, then the alpha particle, it's not that the alpha particle probabilistically decays, but that it's always in what we call the superposition of decay and not decay. And then he says, if it decayed, it kills the cat. If it doesn't decay, then it doesn't kill the cat. And then he pointed out that even the nature of life and death is brought into question in quantum mechanics, because without observing, this cat is in what we call an entangled state with the nucleus. So quantum mechanics says that it's never definite whether the decay took place or not, so the state of the cat is never firmly defined. We can move this into an informational paradigm. So if the particle decays, this is like a NOT operation. You know, we flip a 0 to a 1 or a 1 to a 0. If it goes through roughly the half-life, then it's in a superposition of having decayed and not having decayed. And this is what we would call the square root of a knot. If you do the square root of a knot twice, you square it, then you get a knot operation. So this idea that radioactive decay can move from no knot operation to a knot in a continuous fashion is one of the quantum logic gates that we take advantage of. And then if the decay takes place and the cat dies, or no decay and no death, this is an exclusive OR operation. We call this a controlled NOD in our field, but it's essentially an exclusive OR. And if we combine the two, if we say that the nuclear decay takes place roughly the half-life, and then the cat dies only if it decayed, this is just a sequence of quantum logic operations, which is the square root of a NOT followed by an exclusive OR operation. So we're now able to take these philosophical conundrums in quantum mechanics and actually think about writing quantum computing circuits for it. And this is a helpful exercise for me and for many people I know, because it gives us a way of trying to get intuition on quantum computing. Now, that's a thought experiment that goes back, I don't know, 90 years. But nowadays we have, I'm just going to check one last time to see if, no, I've got that wheel of death on my PowerPoint. I can't show it to you. So just be old-fashioned rhetoric. Okay, so then we have a set of commercial quantum computers out there. And I'm hoping later I'll make the slide available somehow so people can view them. But there's various quantum computers out there. Some that I mentioned, Xanadu, that's based in Toronto. This works with light, so it encodes quantum. So instead of encoding quantum information into cats or into musical notes on a piano, Xanadu encodes quantum information into light. IBM has, they have probably one of the most beautiful quantum computers. Once you strip it down, it looks like a gold chandelier. And at the bottom of the chandelier is a chip of superconducting quantum bits. So bits are binary digits. The quantum bits are the quantum version of it that allows the superposition of 0 and 1. And so they're able to use superpositions of where electric charges can take place in order to process quantum information. And then there's others. Honeywell is now into the commercial ion trapping business, same with IonQ and AQ2 in Austria and various others. And so they take an atom, a neutral atom, remove an electron, so then it becomes an ion. The ions are trapped in electric fields. And then essentially this ion has a lot of electrons, but there's one outermost electron, and they can use the energetic state, whether it's in a ground state or energetic state, to control the quantum information. So there's various physical realizations. So the building of quantum computers is moving rapidly. We can see that there's, right now, the stage that we're at is around 100 quantum bits, give or take, say 50 or 60. Some can be very small, like Honeywell. Some can be very large, like D-Waves, with thousands of quantum bits. So we need other measures besides the space, how many quantum bits there are. So in the, another thing we care about is the time. How long can we run it? Technically, the time we can measure by something like circuit depth. So we can think about applying a set of quantum logic gates. Not every quantum computer operates by quantum logic gates. So how we quantify the time to solve the problem is a big topic of debate and important for benchmarking. But we have these different kinds of measures. But essentially, every one of these quantum computers is like comparing apples and oranges. So it's very tough right now to know which quantum computer is better than which one. You'll see a lot of publicity about it. Google had their quantum supremacy claim, which became controversial when IBM had a blog questioning it. And then IBM has been talking about its quantum volume and its exponential growth expectations for quantum volume. And different people have different measures. But the reality right now is that we're at a stage where the theory is very limited in what it can tell us. And so much of the work that goes on in applying quantum computing is based on practical empirical tests. So we essentially take a problem and then we construct an algorithm that we then execute on various commercial quantum computers to see how well the quantum computer can perform, and then we benchmark it. And so there's a lot of groups around the world, both industry and academic, who are trying to figure out to basically test these kinds of quantum computers. One that was noteworthy last year, Volkswagen is an example of a company that publicized the performance of quantum computing for problems related to the mission of their company. There is an object on the web. It's called the Quantum Algorithm Zoo. This is maintained by Stephen Jordan, who works for Microsoft Research. And the Quantum Algorithm Zoo is a comprehensive collection of all quantum algorithms broken down into types. So there's various types of quantum algorithms, and I find that page very useful. I go to it and look it up, and if a new quantum algorithm comes along, it can be uploaded to the site. And so when I personally start to assess whether there's a potential advantage to using quantum computing, I tend to start with the Quantum Algorithm Zoo, refresh myself on which algorithms there are out there, what the claims are, and then take a particular computational problem, undress it to figure out the different components, and then assess how the Quantum Algorithm Zoo can help. At the bottom of it, roughly, there's 3 very valuable quantum algorithms. There's also something known as quantum-inspired algorithms, which are becoming increasingly studied. And quantum-inspired algorithms arise because sometimes we think a quantum algorithm is really good, and then somebody comes up with a classical algorithm that is as good or almost as good, and they're called quantum-inspired because it's a new kind of algorithm that's inspired by considering the quantum method and then adapting the quantum techniques to the classical algorithmic world. But the 3 that I like to break it down into, so one I'll just call search, the second annealing, and the third is factorization. These are kind of applications of the key algorithms. And now I'll explain what I mean. So the search one is often talked about as searching an unstructured database. For more technically, it's a function inversion problem. So there's a function, and then there's one special marked element, and then the idea is to find that marked element. And if there's no structure to the problem, then, and if there's no difficulty in loading the data describing the function to the database, then there can be a quadratic enhancement. And so many of the polynomial speedups have at the heart something known as amplitude amplification, which exploits the capability of inverting a function quadratically faster. The second one I'll mention is the factorization. At the heart of this is a phase estimation problem. So you can imagine a matrix that's unitary. So it's a complex valued matrix. Its complex conjugate of its transpose is equal to its inverse. There's certain special properties. And then its eigenvalues, I know I'm getting mathematically technical, but just to explain briefly, is like e to the I theta, an exponent of a phase. And there can be a sub-exponential speed up to determining these eigenphases for the unitary matrix. It sounds very technical, but that particular algorithm is at the heart of assessing threats of quantum computing for cybersecurity. Essentially, a quantum computer can be really good at period finding, and cryptography, or public key-based cryptography, is based on believing it's hard to find periods. So classically, it's what we call sub-exponential, so it's not quite exponential in cost, but it's almost there. And with a quantum computer using period finding methods, we can get a speed up to some polynomial overhead. But that particular algorithm is at the basis for algorithms that are used, for example, in solving linear equations. And solving linear equations can be extremely useful for machine learning, regression techniques, etc. And then the other one I'll mention is the quantum annealing. And so in computer science, we have satisfiability problems, and these are at the very theoretical core of optimization problems. And so the ideas of quantum annealing is it's a quantum version of the simulated annealing metaheuristic. We heard there's a talk coming up on genetic algorithms. That's an example of a global optimization algorithm. Simulated annealing is another example. And then quantum annealing takes simulated annealing and adds a capability known as quantum tunneling. And the idea of that is that it's used for optimization problems. And D-Wave's computer is an example of a purpose-built quantum computer that's meant to execute quantum annealing. So these are the algorithms, but there's big question marks. The so-called search algorithm with the quadratic speedup has a lot of caveats that come with it, that have to be met in order for it to offer an advantage, and assessing whether a particular computational problem meets those caveats is difficult. You know, you have to kind of analyze everything very carefully and consider that. The phase estimation algorithm, period finding is really good, but finding problems like factorization that are extremely relevant, finding like when we do it with linear equation solvers, etc., there's a set of requirements that can often be too stringent to make it useful for real practical problems. So finding applications of the phase estimation algorithm to linear equation solving and other uses is difficult, and making sure it works well with existing sized quantum computers is also tough. So these are explorations that go on today. We use that kind of algorithm, we see how it performs, we benchmark it, and then we discuss whether it can be improved and how much advantage it offers. Okay, so all of these come with caveats. I don't want to oversell what's going on, but that's the way we're at. Okay. Now, the next slide I would have shown you is borrowed from Gartner, and Gartner is famous for analyzing potential. And Gartner, there's the hype cycle. So and I'll say more about it towards the end. But Gartner did a nice analysis. So they have these beautiful charts, and there's a bubble chart. And in that one, they analyzed the use cases for quantum computing. So I thought I would just take a moment to summarize Gartner's point of view on the use cases. And they talk about quantum computing as being most useful for various scientific problems. And their bubbles that overlap a bit include quantum chemistry, quantum simulation, quantum communication, quantum algorithms, and quantum machine learning. And I'll talk, I'm going to talk in more detail about the quantum machine learning, as I think that is the most potentially disruptive aspect for quantum computing applied to data science. So I'll talk a bit more about that. But Gartner does do the analysis, and Gartner does an analysis of sizes. So they say that in the scale of 100 to, I'm just looking at their slide now, in the scale of say 100 to 200 qubits, they see quantum chemistry as the use cases that can deliver the most benefit. And currently, there's a lot of work going on how quantum chemistry fits to data science. It's not a good fit, but it is the application that people are doing now in order to test and benchmark. Not the application, but the one of the most promising ones for the scale that we currently have. And then Gartner talks about optimization and machine learning as being on the hundreds to thousands of qubits. And there are groups that are optimistic that we can hit up to, say the 1,000 qubit level over the next few years. They're based on different companies have their benchmarks. They do they do prognosticating based on the current rate of progress, and then they are able to show that they can extrapolate forward on basically how much depth, that's the runtime of the quantum computer, and how many qubits. So if you take the Gartner prediction seriously, then we're not quite at the point where we can solve a useful problem in machine learning or in optimization. We can do toy problems, but it's a few years down the road, and then the idea is to get quantum ready. Now, of course, nobody's guaranteeing this is going to work, and there are big scientific questions existing, but it is prudent at this point to understand the disruptive capability for quantum and to be ready for that disruptive capability if it materializes. So let's go through what in business is called the vertical. So I'm going to now talk about a paper that just came out. It's in the European Physical Journal for Quantum Technology, and it's written by people from Toronto, here in Toronto. So there's an effort known as CDL, Creative Destruction Laboratory. It's based, it's at a number of different universities, founded at the University of Toronto. And then there's two business professors involved, Francesco Bova and Avi Goldfarb, who've led a quantum stream. So it's a stream that's dedicated to fostering startups for quantum technology. And the scientific lead on it is Roger Melko, who's at the University of Waterloo and the Perimeter Institute. And their paper that just came out a couple weeks ago is called commercial applications of quantum computing. So I just want to take a moment to talk about the verticals. So the vertical in business language is really just aspiring to what is the goal that would lead to product or service that can, I suppose, generate profit. And so they aver in their article that that the commercial application in quantum computing is essentially based on discrete or combinatorial optimization. And combinatorial optimization is very much supported by the quantum annealing direction, the satisfiability problem. And so they've picked 3 verticals that are related to combinatorial optimization. And I'll tell you what they are. So the first one that they mention is the materials and pharmaceuticals. And so this is the idea of quantum chemistry, that in a sense, in order to do synthetic chemistry, to build molecules that serve particular purposes, if we want to do it theoretically, the properties of the molecule are based on their lowest energy state. So you start with some description of the atoms, then you imagine bringing them together into a conglomerated molecule, and the optimization comes in by just imagining every possible configuration of the atoms that bring it to the lowest energy state. And I can't help but mention a non-quantum thing that just emerged recently. And the non-quantum thing is there's a very famous old problem known as protein folding. And then there used to be these folding at home efforts where you could, if you had your computer at home, you could, instead of letting it go to sleep, you could let it run in the background to help fold protein. And this is a similar type of thing. It's combinatorial. It's trying to find the lowest energy state. And remarkably, through artificial intelligence techniques, the protein folding problem seems to have been solved. So one of the things I never thought I'd see in my lifetime is about that. And so our techniques in combinatorial optimization seem to be growing quite dramatically with great scientific breakthroughs. And then the question in the quantum computing world is whether a quantum computer can help with this protein, with kinds of problems to do with designer molecules with applications to pharmaceuticals. You can imagine in our time of COVID that we could have even better and better designs of molecules that would be used for vaccines. The second vertical they identify is banking and finance. And for that one, they picked the portfolio management problem. And so the idea of the portfolio management problem is that you have an investment portfolio, you break it down into different asset groups like shares, property, cash, bonds. And then every once in a while you shuffle it. Every time you shuffle your investment to keep it balanced, it costs some money. And so it turns into an optimization problem. And the idea that quantum computing could enhance that is at the core of what they're saying could be the second vertical. And then the third one is the advanced manufacturing aspect. And this is the idea of predicting rare failures. So we can use machine learning in order to recognize patterns and then identify outliers and use the outliers to predict failures. And then this can help in operating machinery. And then the idea is that the hope is that some aspect of quantum computing would deliver a far more sensitive, accurate version that would be able to predict rare failures if regular computing doesn't work. So that's what they write about in their article. And they just go through these different aspects. And as I said, the heart of it is really whether quantum computing can advance the combinatorial optimization aspect significantly. And that's an open question. Okay, so let me go on. Now, there's another article, coincidentally by another person in Toronto, Nathan Wiebe, who just joined the University of Toronto faculty. He's jointly appointed between the Departments of Physics and the Department of Computer Science. And he has an article that came out in the New Journal of Physics a few months ago. It's the September 2020 issue. And he wrote an interesting article called, it's a perspective article. So it's just an article where he has free rein to muse about the state of the field and where it's going. And his article is called Key Questions for the Quantum Machine Learner to Ask Themselves. So if you read the article, it goes through, it's kind of him wrestling with what is the community doing on quantum machine learning? Where is it going? What are the things that we should be thinking about? And I like his article a lot because there's the kind of this current that flows in a community, so we as a community will address the kinds of questions that, we think everybody's interested in, and that helps us get papers that write about things, and we feel we're advancing the field, and we don't spend so much time wrestling with the inner demons about, what are the big things, what should we be thinking about that we might put to the side because they're hard and they're put in the to-do later box. So he writes about that, and I don't summarize the whole article, but I just wanted to summarize the key points that he says. So first of all, he talks about, he asked the question, what is quantum machine learning? And in the quantum field, we have this tendency to just put the word quantum in front of things. So it's easy to do. Everything, we could talk about anything. You can look up things like quantum consciousness if you want, that there's this whole idea that there are things, and then if we replace the fundamental rules by quantum mechanics, then we put the word quantum in front. But it's never straightforward to do that. We need to deconstruct and figure out what it means. So when Nathan asks what quantum enhanced machine learning is, he does it more from an anthropological framework. What does this group of people think? Like, what do they tell him they think it is? So he refers to the most common answer. So the first thing is that it's some quantum enhanced system, device, so platform that delivers an advantage. So the idea for many is that quantum machine learning is some quantum system, hardware and software, and it has an advantage. And what is the typical advantage? Well, the typical advantage is it will compute faster in some way. Now, we have to be careful with the word faster, because we can, computers get faster and faster anyway, simply by hardware improvements. We can put more transistors on the chip, we can speed up the process, we can change the medium. So the faster in this case means fewer arithmetic steps. So if you count your basic arithmetic steps, it's fewer. And more importantly, it's how it scales. As your problem gets more difficult, the growth in the number of arithmetic steps shouldn't grow too fast. And it has to have a well-defined application. For example, training. So if we do supervised learning, we have a data set, we need to involve that in training. And if the training process can be reduced in its complexity, the number of arithmetic steps, that's an advantage. Or it could be classification. And I mentioned to you about the rare failure prediction. And so in that case, we can classify and see, is it of the type that will lead to a failure or not? And so the idea of that kind of quantum machine learning is what I would think of as quantum enhanced machine learning. We take existing machine learning, plug in a quantum box with quantum software, and ask whether it delivers a complexity advantage. Another one is the sampling. So sampling is very expensive for machine learning type applications, that we sample again and again the process and come to some conclusions. If quantum computing could have a box that lowers the sampling complexity, that would be an advantage. Another aspect of this quantum enhanced machine learning would be data models. So the idea of data models, the most primitive one is probably linear regression, where we just have a set of points. We can think of a set of points on a scatter plot and then have a best fit line, and then use the best fit line to predict the future. And in fact, when I talk about how big a quantum computer will be a few years down the road, these are based on these kind of regression methods where we look at a trend line today and then we forecast what the size will be in the future. And so then the idea is that instead of doing that, we can go to richer data models. And the richer data models are what are inherent in neural networks and other things. That there are different ways to represent the data that can be compressed in some fashion and make better access. So the question is whether we can use a quantum computer for other kinds of data representation and exploit those data models. And so in a sense, the fitting to the best line, we're fitting to some quantum description, and we hope that somehow that quantum description will lead to much more efficient fitting. And then the final one that Nathan mentions in this is the very pragmatic data science driven version, which is optimizing a test loss function. So this becomes an optimization problem, and then we can talk about optimizing the loss function. And instead of optimizing it by classical algorithms, we can think of annealing or variational methods or running it on some sort of quantum computer, and then hoping that the quantum computer will optimize better. So that's one group. And then the next group is really what Nathan identifies is the quantum device to classify or extract features. So then this is the idea that somehow, and I mentioned earlier when I talked about the different types of data science, just the data representation is important. So this direction is really about how to represent the data in a quantum computer and how to measure. And the representation could be done with a Boltzmann machine or a neural network as a way to do it. We replace it by a quantum version. So we write it on a quantum version, but then we do what's called hybrid. We'll then we'll do a search by changing, say, the strengths of couplings in a Boltzmann machine, and then test whether we're getting better or worse, and try to use the quantum enhancements in that representation to converge faster to a good description of the quantum data. And then there's quantum algorithm techniques. A famous one is the principal component analysis that came out several years ago that hoped for an exponential advantage. This is actually a very famous case where a couple of years ago, then there was the quantum-inspired algorithm. So by carefully reposing the problem, it turned out that there was not the sub-exponential advantage of principal component analysis. And these are cases where these are actually very tricky things. We're taking the classical algorithms, posing it in a quantum way, and then assessing whether there's an advantage. And the advantage always has to be over every possible classical algorithm, not just the existing one. And so if you find a better classical algorithm, that's the quantum-inspired part, and it reduces the quantum advantage. It's bad in the sense that the quantum advantage disappears, but it's good in the sense that it gave fresh thinking to how to defeat the quantum advantage. And then another one, which manifests a lot in foreseeable quantum machine learning techniques, is that quadratic advantage. I mentioned to you the function inversion problem, commonly called unstructured search in this setting. And the idea is that somehow if we can directly map data into quantum data in the machine learning context, then there might be a way to exploit this quadratic advantage to be able to enhance quantum machine learning performance. Okay, and I'm aware that time's running out. Sorry for the late start and the technicalities. So I wanted to just, I'll go into the wrap-up phase, and I just want to mention there's a nice article that came out recently from Tech Republic. So if you go to techrepublic.com, they have an article, and they just interviewed 6 experts, and they wanted to get quantum computing predictions for 2021. So I just wanted to highlight that to give you a state of play. So I've been saying in a few years this will happen. I have my own opinions on what's going to happen in 2021, but I feel I'd rather defer to Tech Republic's experts on this. So I'll tell you what they said. They interviewed particular individuals. I don't mention their names, but they're representing various companies. And so the IBM person foreshadows for 2021 that their quantum computer, and they have about 29 quantum computers now, and so there's thousands or tens of thousands of users. There's lots of access to this, and they're expecting that the quantum computers will reach 127 qubits. And perhaps more importantly, the interface with the classical side. So what happens is if you run a quantum algorithm, you want to allocate as much as possible to the classical aspect as possible. It's cheaper and faster for a lot of calculations. So they're hybridizing, which means not only are they reaching 127 qubits with a lot of gates, but the hybridization means that the load on the quantum computer for running the algorithms goes down, so you can squeeze more quantum juice out of their quantum computer. So that's what they're foreshadowing. And 127 qubits is really interesting. This is the supremacy idea. We've moved well beyond the point where, if quantum computers are simulatable by classical computers, in a sense, they're not interesting because we can just run simulations of quantum computers and see what happens. And that makes them somewhat predictive. Expensive to predict, but predictive. And we're moving well beyond that point. 2021, it looks like we're going to be well beyond that point. And that means that the quantum computers could hold surprises, and it's less easy to predict the value. Gartner was interviewed, and I mentioned Gartner before. And so Gartner talks about the real move being the cloud providers. So Amazon Web Services, Azure, and others are incorporating quantum capability into what they're doing. And so the idea is that I mentioned early that right now it's a little bit difficult working on quantum computing because you have to learn every commercial system out there and adapt. And what I think Gartner is referring to, and I see this myself, is a move by players into the area where a potential user can go to the cloud provider, and then there will be expertise there to be able to run sub-algorithms quantumly on different platforms to assess performance. And so it takes it drops the barrier for companies to be able to, for companies, academics, general public, to be able to test these things. So the ability to use this kind of software is growing like wildfire. A lot of people are learning how to use it. The access to the quantum computers is growing. So these cloud providers might enter as intermediaries. There's a company called KnowBe4, Knowbe, and then the number 4. And their highlight of 2021 is, and not surprising for the nature of the company, is the threat aspect. And this is that, so the person from that company said that quantum computing in 2021 would break traditional public key crypto. I don't think it's going to happen in 2021. I think it's significantly further down the road, but I said I'm deferring to expertise in this article. And then it highlights an area known as post-quantum crypto. So what happens is in data science, the data storage is very important. So how the data are stored, and the cryptographic methods, even related to that or communicating with the cloud and all the rest, could be threatened by quantum computers. The trend nowadays, so there's a standard being developed in the United States, NIST, National Institute for Standards and Technology, FIPS 140-3, you can search it. And this is the idea to get cybersecurity quantum ready by looking for problems that are easy to check the answer, but hard to solve, not just for a classical computer, but for a quantum computer. And such efforts are still mathematical. They don't require quantum technology. And further down the road, we have quantum key distribution, which is being co-developed with quantum computers, and that would provide the long-term goal. So KnowBe4 is saying that they expect that existing public key crypto will be broken into 2021. If they're right, then the urgency of protecting data from quantum computer threats rises a lot. It becomes instead of strategic planning, it's now a tactical issue. Another company, Lux, Lux, is the person from that company says that the key advance is optimizing quantum hardware to reduce resource needs. I think of this like the compiler level. So, you have good qubits and bad qubits and good gates and bad gates, so good and bad logic gates. And some things can be done classically. And there's a huge amount of work going on to optimize, to know where to use your best qubits, what to allocate for classical algorithms, how to optimize the performance. Maybe even quantum optimization would be used on the compiler level. And so they're saying that's the big advance. And that's what I call squeezing the quantum juice. So the idea is that they're saying the big highlight will be that we'll be able to squeeze more quantum juice out of our quantum computer, significantly so in 2021. And then the last one I mentioned here is Forrester, the company Forrester, and the person from Forrester talks about the trough of disillusionment. And I'm sorry I can't show you a Gartner hype cycle, but in the Gartner hype cycle, there's a rise of expectations, and then there's this trough of disillusionment where people are disappointed by the outcome, and then there's a plateau after where things get better. So when Forrester is saying there's a trough of disillusionment, what the company Forrester is saying is that our expectations could be too high, but the trough of disillusionment doesn't mean it's over. It just means that we recalibrate our expectations. So that covers what I wanted to talk about. I apologize that the PowerPoint froze up and I couldn't show it to you. I hope that my old-fashioned rhetoric worked, and if there's a chance to take questions, I'm happy to do so.
Thank you, Professor Sanders, for a very riveting talk, a very lucid and vivid exposition. And I feel that this is the way public lecture should be done in the first case, is just oratory and rhetoric rather than visual aids and PowerPoints. But again, kudos to you for just fantastic resilience and just showing a great talk. So before I get to a couple of the questions, I have a question myself. It's interesting. You talked about sort of the practical aspects, Professor Sanders, of quantum computing for data science, and you talked about speed ups. And certainly, you said we have to be careful when we talk about faster, because faster can mean different things in different contexts. I suppose one question I have for you, Professor Sanders, is from a practical perspective. When we think about an end-to-end data science pipeline, there's data engineering, then there's the model learning, and then there's certainly the prediction, the inference. Uh, Even though the computational part may be fast in the model learning and then making the predictions, one would argue, but what about the data engineering piece? Where are we right now in terms of libraries, in terms of easily, relatively speaking, packages to prep the data to make them ready for quantum computational types of data science scenarios?
Yeah, that's great. At the moment, we're still at we're at a primitive stage where there are algorithms out there that can be used for subparts. So the way I think about it is that the data science pipeline doesn't change at the moment. It's just that whole sequence. But then what happens is, I don't know, suppose that you're using a support vector machine and you need to solve some system of linear equations, then that just becomes a subroutine that's called to a quantum computer. So at the moment, the way it works is very clunky. It's that we just do the whole data science pipeline, and then we just solve key points quantumly when we need to. The dream would be that everything is quantum. So what would be lovely is that even at the data acquisition stage, so you imagine, that there's some way of gathering data, and that the data is piped directly into quantum data storage. So I mentioned early on about the musical idea and the two chords and that. So you can imagine that if you think of the data, each data point is being a key in the on the piano, and you can just press them all at once and get this cacophonous sound and somehow process. That would be great. This quantum RAM processing, and then process everything in a quantum computer and then get the output. But even on a fundamental and conceptual level, we're not even clear how to do all that stuff. So there's big academic scientific problems existing on how to be able to do it. So my short answer to your question is that in the shorter term, it's really asking whether optimizing a test function or solving a system of linear equations, allocating those to a quantum computer in a hybrid setting where the classical and the quantum computer work together. That's the testing phase we're at. And then we really just need to benchmark against what we care about. So we might not care if that sub-algorithm has a significant reduction in the number of steps, because there might be another overhead. So we just run the whole thing with these quantum sub-algorithms, and then we benchmark accuracy, speed, whatever we want, based on the natural performance metrics for the task at hand. So it's a very complicated issue that's going to take a bit of time to resolve.
Thank you, Barry, for that. Thank you, Professor Sanders. So a quick question and a comment from the audience. So there was a comment about the physical stability of the qubits, as well as their ability, or just the fact that they decohere too quickly. And then a question, which was that, do you believe that we'd be able to prolong the quantum coherence time to preserve information and run the algorithms for longer?
Right. Okay. So this is, so I've been in the quantum computing field a long time, a quarter century or longer, and actually longer. And the thing that we cared about for a very long time, and I still care about, is the decoherence. And this is the idea that the classical world we live in, we can get by without knowing quantum mechanics, because quantum mechanics is very fragile. So the idea of decoherence is that every interesting quantum thing breaks down on some length or time scale. And we have this whole theoretical framework and plan over a long term to do what's called quantum error correction and fault tolerance, so that we're able to, if we can make the components good enough, we're able to beat this decoherence problem and be able to build quantum computers. But the commercial quantum computing is totally avoiding that right now. They're saying, let's allow decoherence to take place and just build and see how far we can push it. And in a sense, this is bad because it removes any exponential advantage. So the idea that quantum computer is not coherent, this means that longer term, the current approach we follow is doomed to fail. And this is what I said about the squeezing the quantum juice out of it. So then we want to reduce the decoherence, and we do it, and I'll give you an example. Like if we build a superconducting quantum computer, the decoherence can be due to the impurity of the superconducting material. So we can make better materials, or we can start to figure out where stray electric fields are that are causing things, or whatever. We can, there's all kinds of materials and designs issues that can mitigate the decoherence and stretch it further. So we know we'll hit a dead end, but the hope is that we can get hundreds or thousands of qubits with enough coherence that it can offer a quantum advantage. And as time goes on, if we're able to start to incorporate quantum error correction that's based on a coding principle and then detecting and correcting errors, then that's the leap we need to get us to the longer term, where quantum computers can get to the millions of qubits.
Thank you, Professor Sanders. So just in the interest of time, we have a lot of interesting comments in the, a lot of statements and questions in the comment section, but I'll maybe show you quick to get your reaction, and then we can close it out. One is, and let me show you both first. So are there any courses or trainings that you can suggest for online learning in this area? And I would say related, but not exactly the same. Are there any libraries for ML algorithms in quantum computers that are accessible for developers to explore AI opportunities?
Yeah, so I'm glad you asked that. So I mentioned that there's different software frameworks for various quantum computers. So yes, there's a lot out there. The stage that the quantum computer companies are at right now is they want as many people to use their system as possible. And so if you want to play around with things, these quantum computer companies are very open to that. They try to go open source. I mean, I can mention Xanadu has what's called Strawberry Fields. You can use theirs. You run their quantum algorithms on simulators, and they have a lot of exercise you can run through. IBM has people going out around the world training in camps. It's Qiskit, Qiskit, and various other companies. I won't list them all here, but if you go to the company website and then you try to use their software, you can do it. You can run it on the simulators, play with it, and see what happens. And it's interesting. So for me, in my background, I would have said, here's a textbook, read it, learn it, do the exercises theoretically. But the new generation coming on board, many of you, and probably you who asked the question, prefer to learn hands-on. Let's write code, see what happens. And it's a perfect time for it because these companies have it. Just go to the various company websites, you'll find the software framework, and then start playing with it. And then if you get a chance to go to something like an IBM camp, take that opportunity. They're run in various places. And all these different software frameworks are interesting in their own right, and it's worth playing with each one.
Thank you, Professor Sanders, for a very thoughtful and thought-provoking talk. We'd love to have you come back. Just in the interest of time, we have to wrap up now. We would love to invite you back and to talk about further advances. You touched on a couple of interesting papers, so maybe in a few months you can come back and give us a more renewed view of the landscape. And thank you so much for taking the time to speak with us today about quantum computing for data science.
Thanks for having me, Vic.
Thank you. Bye for now.